Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 23, 2025, about 4 days ago. The standout result is simple and strong. On ImageNet at 256, it cuts FID from 2.07 to 1.68, while adding less than 0.6% parameters, and training moves faster. The paper is titled, CarFlow, Condition-Aware Reparameterization, aligns source and target for better flow matching. And as we will see later, the implications for model training are quite significant. In short, this paper learns lightweight condition-dependent shifts of the source and/or target to shorten transport, avoids collapse by restricting to shift-only maps, and improves quality on images and toy data. Alright, the intro just established the motivation. Figure 1 contrasts the standard direct mapping with the CarFlow chain that inserts condition-aware maps before and after the velocity field, so the model learns a shorter residual path. The left red source region depicts a single prior that becomes condition-aware via the source map F. The right blue target region shows the aligned latent that is decoded with G inverse. The bottom dotted path highlights the shorter transport under CarFlow. While the previous figure sketched how condition-aware shifts shorten the path. Table 1 lists the zero-cost collapse modes when maps are unrestricted, which means the optimal velocity becomes affine in Z with gamma and eta, and the distribution collapses. Constant source or target yields delta spikes at mu0 or mu1. Unbounded source or target scales push toward a uniform distribution. Proportional collapse ties F and G, giving a degenerate constant flow. So Table 1 warned about collapse when maps scale or tie together. Figure 2 shows the learned trajectories on one-dimensional data across baseline, source-only, target-only, and joint variants. The source-only panel relocates the starting region per class, which simplifies early flow, while the target-only panel creates a shared landing zone. The joint panel aligns both ends, so trajectories shorten the most. Thin lines mark sample paths, and dashed bands indicate 3 sigma shifts. Alright, Figure 3 compares training behavior and the learned shifts. The left panel shows Wasserstein distance, dropping fastest for the joint variant, with source-only and target-only close behind, while the baseline plateaus higher. The right panels plot mu0 and mu1 over steps, which stabilize to moderate values for the joint case, so the flow moves less, yet remains class-aware. Together, these curves indicate quicker convergence because the residual path is shorter and the shifts stay balanced. So Figure 3 showed faster convergence for the condition-aware shifts. Table 2 reports average path length from Z0 to Z1 with 2 sigma error bounds, which directly measures how much transport the model must learn. The baseline measures about 1.54. While source only drops to about 0.743, target only to about 0.713, and joint to about 0.712. The tiny plus or minus values confirm stable estimates, and the joint variant achieves the shortest paths overall. So, Table 2 reported shorter paths. Figure 4 diagnoses mode collapse, when scale is also learned. The left plots show the learned scale sigma rapidly shrinking toward 0, and the validation error falling near 0, which signals the trivial zero-cost solution. The source-only panel on the right collapses each class toward its mean, producing narrow spikes. The target-only panel collapses almost everything to a constant, so predicted samples behave nearly uniform, and the flow degenerates. Okay, the previous figure diagnosed collapse once scale was learned. Table 3 reports ImageNet 256 results across metrics, and the table shows broad gains with condition-aware shifts for almost no parameter overhead. The joint shift variant delivers the best scores, cutting FID to about 1.68 with classifier-free guidance and lifting inception score to about 304. The upper block at 400,000 steps already favors joint shift, and the lower 7 million step block confirms the same trend with higher precision and recall. Wrapping up, 2 takeaways stand out. Shift-only, condition-aware reparameterization shortens the residual path the velocity network must learn, and it avoids collapse while delivering better fidelity and faster training with tiny parameter overhead. The broader implication is a simple plugin for diffusion and flow systems that boosts conditional generation efficiency. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.